Okay, here's another very good example here that I often like to put on an exam. Um, and the reason I like it is it's actually a very simple problem, although I think people look at it and they think it's a lot more challenging than it is. Okay, so I've got an op amp, it's 33 kilo ohm resistor on the input, and then I've got a feedback capacitor of 1 microfarad. So the problem has two parts here. So we're going to say find V out at t, so we want an expression for V out at t. And then the second question is how long does it take for the op amp to saturate? And of course what we're going to do here is we're going to assume, the problem will state this on an exam, but assume all initial conditions are 0. Okay, so again we have to do Laplace transform of our circuit here. So of course this becomes 5 over S, and then this capacitor, this of course stays 33 kilo ohms. This becomes 1 over S times 1 microfarad, which would be 1 meg over S. I'm just going to write it as 1 meg for now here. Now, people make this a lot more difficult than it needs to be. And what do I mean by that? Well, let me just put an aside here. I'll probably erase it and then scroll back up. If this is a problem we've examined many times before, let me show you the problem that we've examined many times before. Again, assuming the op amp is ideal here, we've examined this problem and we should all recognize this as an inverting op amp. So what does this do here? Well, it inverts, right? So we know that the output voltage here is just the feedback resistor over the input resistance times the input voltage, and it's a negative because we are inverting it. So we would have that this is just 6 kilo ohms over 3 kilo ohms. I'm sorry, 2 kilo ohms, I got ahead of myself. Times 3 volts, which would be 9 volts. So that's something we should all be familiar with. So I'm going to erase this now and scroll back up to what we have here. Okay, so scroll back up here. So this here I want to emphasize, this is in an inverting configuration. Now I'm emphasizing that it's in an inverting configuration. This is not an inverting op amp. It does do an inversion, but it's not an inverting op amp. Like the one we just showed. However, because it's in an inverting configuration, we can still use the same tools that we know here, because remember, everything in the Laplace domain behaves as if they are resistors. And so what we end up getting here is we get then that we have that the output voltage in the S domain is going to be the feedback impedance in the S domain over the input impedance in the S domain times the input voltage in the S domain. So let's see what we get when we do that. We get ZF being 1 meg over s divided by 33k times 5 over s. Now doing a little bit of arithmetic here, 1 meg divided by 33 kiloohms gets me, and then times that by 5. Actually, I'll wait to do that a second. We get 30.3 over s times 5 over s. And so when we do this one here, we have 30.3 times 5, which is, I forgot one very important thing here. There's a negative on all of these. That's extremely important. So negative then 151.5 over s squared. But believe it or not, we're done. We don't even need to do any other work. We know what v out of t is, because again, using your Laplace transforms table, what do we have here? 1 over s squared just goes back to t. So we have here that v out at t is equal to negative 151.5 t, and then it seems weird to also then write u at t, but again, remember we write u at t to kind of emphasize that we're starting at time equals 0. So that's the answer. That's it. So an op-amp problem that looks like it could be complicated turns out to be straightforward. Now, the other thing we should recognize here is this is something that we should recognize from circuits 1, because this is a circuit that we did not analyze in great detail, but we noticed that this was something we called that was an integrator. And you've actually probably examined this in the lab where you created an integrator, so to create a triangle wave. And so that's what we have here, because if you integrate just a constant, 5 is just a constant, you get a constant times t. Now, why are we getting this 151.5 instead of just 5? Well, that has to do with the fact that we have a value of 1 microfarad for the capacitance and 33 k ohm for the resistance. We're going to be getting some kind of gain going out of that. So part A, this is it for part A. Now, this should be for t less than t0. t0 is where op-amp saturates. But that's what part B is asking us to find. But if we want to be technically correct, now I would accept this as an answer. But we do have to be careful because it is going to saturate that op-amp. And well, part B, when does it saturate? Well, that's easy enough to figure out. It's going to saturate down to, what was my power supply on this? Negative 10. So it's going to saturate down to negative 10. So we're going to have negative 10 is equal to negative 151.5 t. And I hope that we are all at a level that we can solve this equation. If not, then I have some serious concerns about us being in electrical engineering. And if I typed it into my calculator correctly, I might get you the answer. And I get that this is 66 milliseconds. So it's going to saturate at 66 milliseconds. So that's it for this problem. So definitely much easier than the last example. And as I said, I often like to put ones on here like this. Now there's variations I can do there. I could put a capacitor here. And actually that's a good one here. Before we even do it, let me just show you. I'm not going to do it here. This is a good one for you to do on your own here. Take a look at this one, for instance. fact, I'm going to give you a couple ones you should look at here. So we'll make these numbers nice, easy ones to deal with. We'll do 1 microfarad, and we'll do 10 kilo ohms. And we'll power supply this 10 volts and negative 10 volts again. Actually, I'm going to do 100 kilo ohms, I think is what I want to do. Yeah, I'll do 100 kilo ohms. Yeah. And then VG, look at several different possibilities. 0.2 T, VG is 0.3 e to the negative 0.2 t. And one more if you're wanting to really explore some things, 0.2 cosine of, we'll just do 10t for simplicity. Should look at those because this one here, if you remember, is a differential op amp. In other words, it takes derivatives of functions. So you should look at what you get as an output from these here using Laplace transforms. Yeah, it'll be pretty cool. So, all right, but I'll let you guys explore that, and we will end the lecture here.